Okay, I think we'll get started. So hello and welcome everybody. Just, these people in. My name is Andrew Dine, and I'm a member of the Solenis team who has been working on developing our geothermal power technology portfolio over the last few years. In my spare time, I'm also the commercial manager for Solenis operations in New Zealand. I want to first of all thank you all for attending and investing some of your valuable time today to learn some more about some exciting developments we've been working on for scale control in geothermal power systems. So today's webinar will consist of two presentations on the modelling, monitoring and control of the two most challenging deposit species found in geothermal power, those being calcite and silica. This will take approximately 45 minutes, leaving 15-20 minutes for questions and further discussion. I would ask please that today's session will be recorded and the recording will be available on solenis.com within the next 2 to 3 days. Please ensure your microphones are muted, and also we'd ask that you please hold all your questions until after the two presentations, and we ask that you submit these questions via Microsoft Teams meeting chat function. You're also very welcome to contact us anytime after today's webinar, either by my email, which I'll share with you later on in the presentation, or through solenis.com. First of all, though, a little bit about Solenis. So Solenis is a global specialty chemical company that has been adding value to both consumer and industrial markets for over 100 years for its various legacy organisations, and you may be familiar with brands such as Drew Industrial, Betts Laboratories, Hercules, Stockhausen, Ashland Water Technologies, and most recently BASF Paper and Water Division. We're certainly proud to be leaders in our strategic markets and operate globally in about 120 countries, employ some 6,000 people, and produce our technologies from 47 manufacturing plants across 5 continents. Our reason for existing is to solve tough water treatment and process improvement challenges through the core elements of people, experience and technology. And by doing so, we help our customers meet their operational and sustainability goals. The geothermal power industry is very much a strategic market for Solenis, and over the last 3 years, we have carried out extensive voice of customer research, invested over $2.5 million in R&D to develop solutions to the problems and challenges highlighted by the industry to us. As a result, we have developed and validated a portfolio of novel and industry-leading technologies, some of which we're excited to be sharing with you today. So today's first presenter is Dr. Mike Bloomley, who will be covering calcite management and control. Mike is the group leader of Solenis Water Applications Laboratory in Wilmington, Delaware. Over the past 3 years, Michael and his team focused on the research, development and commercialization of new calcite scale inhibitors and online cleaning methods for geothermal power producers. Additionally, Michael regularly provides technical modelling support for geothermal, cooling water, reverse osmosis and mining applications around the world. Michael has a bachelor's degree and a master's degree in chemical engineering from Case Western Reserve University in Cleveland, Ohio, as well as a doctoral degree in chemical engineering from the University of Minnesota in the Twin Cities of Minneapolis and St. Paul, Minnesota. So Michael, it's a pleasure to hand over to you.
Thank you, Andrew, for that kind introduction. And thank you to all of you that are on the call today. I'm very happy and excited to join you from my office here in Wilmington, Delaware, and share with you some of the work that the Solenis team has done over the past several years with the focus on calcium carbonate scale control. So while mineral scaling can occur in most parts of a geothermal power plant, calcium carbonate deposition primarily occurs in the production wells and separators, which are circled here on this schematic. And in untreated or poorly treated systems, calcium carbonate formation can rapidly occur, I have a picture here of an untreated production well. And in these untreated or poorly treated systems, calcium carbonate deposition can result in loss of brine flow and ultimately a loss in power generation for our geothermal customers. Now, calcium carbonate formation in production wells is fairly well known, both from a process and chemistry standpoint. And calcite typically forms due to flashing in the production well. So in the schematic on the left, we have a picture of a calcite blockage from two different production wells, and a schematic, a picture of where the flash points are. And again, the calcite deposition occurs typically just above the flash point. So when flashing occurs in a production well, this does two things. It increases the brine pH, and it also increases the ion concentrations. Both are driving forces towards calcium carbonate deposition. And this can be a very rapid, localized deposition process occurring within 50 meters or so of that flash point within the production well. And again, here's another picture where you can see calcite scaling has occurred and a well bore in this deposition occurred just in the matter of weeks. So because we understand the chemistry behind this process quite well, we can model it with pretty good accuracy. And one of the software programs that has been utilized in the geothermal industry is Watch. This has been around for over 40 years now. And it's a very powerful piece of software, but it's a standalone software platform that has to be installed locally on your computer. And it can be quite time consuming to use, especially when modeling many different production wells. And really, it lacks some features such as charting capabilities that would be nice to have. So as an improvement over the past year or so, Solenis has developed a web-based user interface that utilizes Watch, the thermodynamic modeling of Watch in the background. We have branded this tool as the GeoSol performance modeling tool. And with this web-based tool, users can much more quickly enter their data, navigate through simulations, and run through different scenarios, and it can automatically generate charts as well. So this GeoSol performance modeling tool is free of charge to anyone that is interested in utilizing it, any customers or prospective customers of Solenis. It can be accessed off of Solenis's geothermal power website using the web address shown at the bottom here. And again, this is a free tool that we would like everyone to have a chance to utilize. And with this tool, users can model calcite saturation index. So here I have an example of the CSI as a function of flash temperature. And again, users can use this to quickly assess whether existing or future production wells are likely to form calcium carbonate. And a useful rule of thumb is if the CSI is greater than 0.5, it's definitely supersaturated, scaling's likely, and a treatment strategy is needed. So now that we've covered some of the basics of calcium carbonate scale formation, how do we prevent it? What are some mitigation strategies? Well, one very effective one that's widely used globally are capillary dosing of anti-scalants. So on the drawing on the left here, we are dosing an anti-scalant downhole. And one thing that is very important is to ensure that we're dosing that anti-scalant below the flash point. So the flash point is here in this picture, and we have the capillary dosing system dosing below that flash point. So there are many anti-scalants out there commercially used in a wide range of applications. And there are several key factors that we should consider when choosing an anti-scalant for a geothermal application. The first being thermal stability. In some parts of the world, there are very high enthalpy production wells greater than 300 degrees Celsius. Certain chemistries will just not tolerate that type of temperature and will degrade, resulting in loss of performance and potentially deposition from the byproducts of the anti-scalant itself. Second, we really should consider the chemistry and its tolerance for the brine chemistry. And one thing that Solenis has spent a lot of time focusing on is the impact of metals such as aluminum and iron, which are commonly found in geothermal brines, and their impact on the performance of calcium carbonate anti-scalants. And I'll show you some data in that area a little bit later on. And lastly, we want to identify products that are high performing for calcium carbonate scale prevention and provide the greatest performance possible at the lowest dosage possible. And so over the past 3 years or so, Solenis has spent an immense amount of time synthesizing new molecules and looking at them both in the laboratory and out in the field. And we have now developed a very nice portfolio of robust, effective calcium carbonate anti-scalants. And I'll go through some of the testing that was done in the laboratory first to identify these chemistries. So the first testing that we did was here in Wilmington, and this is a modified NACE test. So the NACE test is commonly used in geothermal applications for calcium carbonate inhibition, but here we've modified it a little bit, so we actually have a higher CSI, a higher calcite saturation index. We also did some thermal stability testing of our products using the procedure shown here on the left, 250 degrees C for 1 hour. And we not only looked at over 30 commercial and developmental products, but we also did benchmarking against products that are currently used by geothermal power customers globally. So in this chart here, I'm comparing relative calcite inhibition performance for two benchmark products, A and B, against several Solenis developed products, C, D, and E. And a couple of things to note. One, in all cases, there's a large increase in performance from the lowest dosage of 1.5 ppm to the next dosage of 5 ppm. So there is a threshold inhibition, a certain amount of product that must be dosed to really get any significant performance for any of these products. The second thing I'll note is that Solenis was able to identify several products such as Inhibitor C that had superior calcite inhibition performance compared to our benchmark chemistries. And Inhibitor C we thought was especially effective and had great thermal stability as well. In addition to doing laboratory testing in Wilmington, we also handed some samples over to GNS in Taupo, New Zealand for some third-party testing. So in this case, GNS did a standard NACE test, and they had their own thermal stability protocol, which is shown here at the bottom left, 300 degrees C for 4 hours. So quite a thermally stressed process here. Once again, I'm comparing some benchmark products, A and B, against the Solenis products, C, D, and E. And in this case, we're looking at samples that have been thermally treated compared to those that have not. And once again, we see very, very good performance from the Solenis products, C, D, and E, without thermal treatment. They all have superior performance as compared to the benchmark chemistries of A and B. But one thing that we noted in this testing was inhibitor E did show a pretty significant drop in performance after thermal treatment. So while inhibitor E we feel is a very effective product for lower enthalpy systems, this is one that we will not use in higher enthalpy production wells. But we were quite happy with this testing. And again, the result was the identification of highly effective calcium carbonate scale inhibitors. Now, I mentioned before the impact of metals and geothermal brines was something that we wanted to also take a close look at. So aluminum and iron are quite common in geothermal brines. And it's been known that these multivalent metal ions can poison most anti-scalant inhibitors. This reduces the effectiveness of the anti-scalant, and thus we need to increase our product dosage if we still want to prevent calcium carbonate deposition. Now, one thing that we heard from many geothermal customers globally was that in some cases, incumbent anti-scalant programs were not successful, and we think in many cases that was due to not accounting for these metals that are in the geothermal brine. And during the course of our lab testing, we did identify some benchmark chemistries that were pretty poor in the presence of metal ions, and then we were successful at identifying chemistries that were more metal tolerant and superior to these benchmark chemistries. So in this example here, I'm comparing a GeoSol product from Solenis, GS9200, versus that inhibitor B benchmark chemistry. And again, I'm looking at calcite performance, but this time in the presence of 0 to 1 ppm of aluminum. So the first thing I'll note is, once again, the GS9200 has superior performance even in the absence of aluminum. But again, it maintains that effective performance even in the presence of 1 ppm of aluminum, where there is a more noticeable drop-off with the inhibitor B chemistry. Now, we also did this type of testing with iron, and we found that iron was also very detrimental towards the efficacy of some products. So here we have calcite performance in the presence of 0 to 1 ppm of iron. Here we have another commercial GeoSol product from Solenis. Once again, there is a decline in performance in the presence of iron, but this is much superior as compared to the inhibitor B, which almost totally loses its performance in the presence of just 1 ppm of iron. And so now that we've done this laboratory testing, now that we've been able to quantify the impact of these metals, we can now utilize that in our modeling program, in our dosage recommendations as well. So once we completed this laboratory testing, of course, we want to take this out into the field and see how our chemistries perform there. So for the first case study I have to share with you is from a New Zealand geothermal binary plant. In this case, they were using a competitive product at a fairly high dosage for their production wells. Their brine had about 0.6 ppm of aluminum. And so we used our GeoSol performance modeling tool you can see an example of a calcite saturation index versus flash temperature chart here. And then we chose an anti-scalant based on the thermal stability profile and aluminum tolerance of the chemistry. So using what we had learned from the field, we recommended a total dosage of 4 ppm of product. 3 ppm of this comes from the calcite saturation index itself, and an additional 1 ppm is needed because of that aluminum that is in the brine. And this is a 33% reduction compared to the incumbent product and a potential cost savings for the customer. The second example I'd like to share with you is from a Central American geothermal power plant. And this case was conducted in conjunction with the customer, Ormat, and this actually resulted in a recent paper at the GRC as well. So if you're interested and would like to learn more about this particular case study, please refer to that paper. But in this example, the customer was having very severe calcite scaling in their production wells. This was resulting in the loss of several megawatts of power, and mechanical cleaning was required on a pretty frequent basis. When we became involved, we suspected that the incumbent product had poor thermal stability, but this was also a very tough brine that had about 1.7 ppm of aluminum present. So once again, using our modeling tools and our knowledge from our laboratory work, we selected an anti-scalant product that had good thermal stability and aluminum tolerance. And we began a trial back in February. And so in this chart, we're looking at calcium concentration measured in the brine over the period of several months. And in these bump tests, in some cases, we are applying an anti-scalant. Those are the blue dots. And in other cases, we turn the anti-scalant dosage off. Those are the orange dots. And we can quickly determine that we do see an effect from applying the anti-scalant. And through this process, we were able to also optimize the dosage. So after this initial trial and some ongoing work with the customer, the wellhead pressure and brine flow rates returned back to their pre-scaling conditions. The customer did some well surveys several months later. There was no scaling detected, and this customer has been using our GeoSol anti-scalant for now 9 months without any issues. And we were able to provide a solution to this customer that was much more effective than their previous chemistry. So with that, I thank you for your attention, and I'll hand it back over to Andrew, who will introduce our next speaker.
Thanks, Mike. Much appreciated. As I indicated before, if you could just hold any questions for Mike to the end of our second presentation. So our second presentation will be presented by Peter Slight, who will discuss silica monitoring and control. Peter has more than 30 years of water treatment experience and regularly provides consultation support to customers around the world in a variety of industries, including power, geothermal power, metals, and chemical processing. During the past 3 years, Peter played an instrumental part in advancing Solenis research and development efforts in scale and corrosion control for geothermal power process. Most recently, he moved into business development at Solenis with a focus on the New Zealand geothermal power industry. Peter has an undergraduate qualifications in chemistry from the University of Auckland in Auckland, New Zealand. So Peter, it's a pleasure to hand over to you.
Thank you very much, Andrew, and hello everyone. I'm just trying to request control of this presentation so that I can advance it, but otherwise I'll be using Andrew's skills, and I'd like to thank Mike as well for his work earlier. And so I'm going to be focusing on silica deposition, and specifically, I will be looking at areas where, in a geothermal power plant where you get deposition and there are you do an analysis of the deposits and you get high levels of silica. So you analyze it and it's pretty much, most of it is all silica. So that's what we're talking about.
Would you like me to control, Peter, or?
Yeah, just advance it, please. I can see my cursor, but I can't advance the slides.
Okay.
Thank you. Okay, so silica deposition, and again, we're talking about high levels of silica. Where does it occur? Well, we know it occurs in production wells, down in the actual formation, if there's flashing in the formation. Normally that's an issue in high enthalpy wells, and of course there's no online treatment that can be used for that because we can't dose the formation. But actually we do have technologies, chemical cleaning technologies that allow us to re-stimulate and dissolve out some of that silica in the formation, which is very interesting. Separators can show silica deposition. Often they get, because that's where you get the initial a lot of flashing and rapid cooling and changes in chemistry. You often get, like, if you get a silica deposit there, it's often more like a silicate deposit, which is not really a focus that I'm going to be talking about today through lack of time more than anything. But certainly in the binary heat exchanges, binary plant heat exchanges where you get brine cooling, you're taking heat out of the brine, it cools down, the solubility of silica reduces, and for sure from there on and then down to the reinjection, that's where you get most of the high silica deposition. Thanks, Andrew. So in these areas, what does silica deposition look like? Got some pictures there for you on the top right, with a screwdriver in there as reference. If you see that sort of white-grey type of deposition, that's classic amorphous silica scaling. Top left, we've got just the pipe that's just over time, just as blocking up with deposition. And in the bottom right, we've got a reinjection pipe work. This is one from Central North Island, New Zealand. And we get like a very unusual and a very interesting deposition there. We call it fence post type scaling, where we actually get like what looks like a whole lot of little fence posts that have been pushed over. And the little posts actually grow into the flow, which is sort of counterintuitive, but that's what they do. And the picture on the lower left there is actually one of those little fence posts that's been removed from where it was attached. And you can see that you just get these little like posts of very high amounts of silica growing into the flow of the brine. So you can imagine that, like, when you start getting these sort of deposits, it really slows down or inhibits the mass flow of brine, and you can end up in situations where it becomes limiting for the power plant because you just can't get rid of the reinjection. What I can't show you a picture, of course, is what happens right down in the reinjection where the brine actually goes back out to the formation. But we know that this silica deposition is actually happening there as well, certainly until the brine can get heated up again and redissolve the silica. Thanks, Andrew. So I think we've got one person at least from Contact Energy online, and they have a power plant in Ohaki in New Zealand. And here's an example of what happens over time with what happened over time with this plant. So this is megawatts production. So when they started the production, eventually you get like a depressurization in the field, so you get a reduction there. But after that, then after a few years, we start getting like the restriction of reinjection system flow, which starts impacting on power production to the point that in like around July or in 2007, 2008, they had to put in more production in reinjection wells. So yeah, we get a loss in power production as silica deposition contributes to that. And certainly in the reinjection wells themselves, the decline is gradual, but then it reaches a point when the things are getting blocked up enough that we actually get quite rapid reduction in flows. Thanks, Andrew. So what's happening from a chemistry point of view? So if I'll just refer you to the sort of the right-hand side of this slide, that when silica becomes oversaturated in a brine, it starts holding hands. That's the way I like to think about it. And as long as we're oversaturated, it just continues until such time as we get polymerized silica formation, and it continues in 3 dimensions, of course, and you end up with silica colloids. And certainly the silica colloids are believed to be what's causing this fence post type scale. Like they physically impact onto the existing deposition and just keep growing it. So that's the takeaway from here. Perhaps the last thing I'd say on here is that the actual polymerization process is catalyzed by hydroxide. In other words, it needs a little bit of OH minus in the water to actually make it go faster. Otherwise, it's a very slow process. Thanks, Andrew. Okay, what about the effect of temperature and pH? Well, silica has normal solubility, so quartz and amorphous silica in the geothermal power plants, what we see is amorphous silica. So what we're saying here is that, like, as the temperature goes cooler, the solubility reduces, and that's why we start seeing deposits in the cooler areas of the geothermal plant. And in terms of pH, there is actually an effect that if like a pH is elevated, like if you could get the pH, or if the pH was naturally up around 9, the solubility of amorphous silica is significantly higher than at, say, neutral. Thanks, Andrew. Okay, so what are we going to do about it? And there are a number of approaches. Thanks, Andrew. And so we've got a few, our area is specialty chemical business. So I'm looking at some chemical approaches here, but the common or known mitigation strategies using chemistry, use of acid to delay sulfuric acid to delay polymerization, like slow the thing down. Use of caustic to increase solubility. I'm not going to go there because people don't use it and because it's expensive. And when you add caustic soda, you actually force the precipitation of other minerals. There's online chemical cleaning. I'll certainly touch on that. And what I want to focus on mainly is scale inhibition. Thanks, Andrew. So acidification, and this is certainly carried out in New Zealand, and people around the world who are online may be using acidification in your plants as well. But the idea is that, like, if you can get the pH of the brine down to about 5, it slows the silica polymerization process down. So that the idea there is that the brine can get through the plant, back down reinjection before large amounts of silica can actually hold hands and start forming deposits. And by the way, it also helps with like calcium, magnesium, and aluminium solubility. So what we see is, well, this is not easy. It's actually not that easy to do reliably. It's expensive. You use large amounts of sulfuric acid. And the chart on the left shows you what happens if you're just out on your pH by even half a pH unit, where the amount of monomeric silica or non-polymerized silica stays very steady at pH 5.5. Sorry, 5.0, but if the pH happens to only be 5.5, like you've underdosed acid a little bit, then you can get rapid polymerization. So you really need to be on your toes to do acidification. And of course, if you dose too much, you'll get to like a free mineral acidity area, and everything down there and up there is all made out of steel, and you can get corrosion. Now, the other effect with acidification is that, like, when acidified brine gets back down to the formation or reinjection formation, depending on the temperatures at the receiving area, the formation can actually neutralize that acidic brine and actually form silica deposition right there in that area. So we're seeing, and we certainly see in New Zealand plants that, like, despite acid dosing, the reinjectivity actually reduces over time. Thanks, Andrew. Okay, so moving on to step 3, which is would be online chemical cleaning, and I'll just refer you to actually our colleague Dr. Logan Muller actually did a webinar on this subject several months ago, and that's available from solenis.com. But basically, it is possible to actually run a online chemical cleaning process into the binary plant or right down into the reinjection system whilst the plant is running. And we've actually developed some techniques and procedures around there that are IP for us. And I certainly refer you to those that webinar. Thanks, Andrew. Okay, so to focus now on silica actual scale inhibitors. So we sort of started with this understanding, and I think this would be true for everyone, that if there was a good silica inhibitor, it would just keep the plant, and reinjection system clean and free flowing over long periods of time, right? That's the goal. It'd be easy to use, no other problems, like easy to apply, no safety considerations for human, no corrosion of the plant, and be economical to use, but also it should ideally allow you to run high megawatt production. In other words, could you actually take more heat out of your geothermal fluid? So that's what we want in the real world. Of course, in our R&D labs, if you can advance, please, Andrew. In our R&D labs, we have to speed things up, obviously. So when we did our studies of silica inhibitors, and it's ongoing, of course, but a good silica inhibitor in the lab will actually minimize silica polymerization, and you can actually test that. You can test how much of the silica is staying there without polymerizing, and it's got to minimize any precipitation of silica-based solids. Look, if you're getting colloid formation, you'll start seeing turbidity over time in your test solutions. So additionally, in the lab, of course, we have to use a synthetic geothermal brine, and we typically run them at about 60 Celsius, because if you get in the lab, if you go too much higher, we're almost under pressure situations. But we certainly do drive up the silica saturation index to 2.5, and that's 2.5 times oversaturated with silica. Thanks, Andrew. So when we started out, we've tested over 100 commercial and developmental products, and what we do in the first run is we just make a supersaturated solution of silica with the inhibitor in there, and see what happens to the amount of measurable monomeric silica over time. So if you have a look at this chart, you'd suggest that the inhibitors that are sort of flatlining across the top, and remember that the time across the bottom is hours, you'd say that like the inhibitors there, sort of 7, 8, and 9, are giving real stability, certainly compared to no inhibitor. So you'd think they're good, right? But what we wanted to be careful about was work that we've done with calcite inhibition, and that Mike's already talked about. Thanks, Andrew. Is what happens in real world situations where there's actually these poison impurities like iron and aluminium. And what we found is quite a dramatic difference here. So same test, exactly the same brine. We had inhibitors that looked good. We added 1 ppm of aluminium to the test solution, and goodness me, they all basically lose pretty much all of their performance. So in other words, there's a strong negative effect if you've just got a little bit, even a small amount of aluminium present in the brine. So we really had to scratch our heads. Thanks, Andrew. And not only did the silica inhibitors not work when there was aluminium, we actually started developing turbidity. And so this chart just shows one inhibitor at 8 at different ppm levels, and in the presence of aluminium, we just got turbidity, and the turbidity increased the higher the dose. So it's just proving a very strong interaction between the aluminium and the potential inhibitor. Thanks, Andrew. So we needed a new approach, and we said, well, maybe there's a combination or complementary actives we can use. We've obviously got to condition the problem metal cations, and aluminium's our major bad actor here. But we've still got to delay polymerization and prevent precipitation. So thanks, Andrew. So what we found was we did find, and this is a subject of intellectual property, and I'll discuss it further, but we did find a combination of inhibitors. We call them here 7 and 11, but we actually managed to, if you have a look at the chart in the middle there, you can see that like over a period of 2 or 3 hours, the silica levels remain constant at what they started, certainly compared to the blank. And the other thing on the right-hand chart is the same combination did not produce any turbidity. So it appears that this combination approach allows us to stop polymerization of the silica and condition or deal with the negative effects of the aluminium. So that was very exciting, and it just shows that, like, we're actually looking at this from an R&D point of view specifically for geothermal. So we haven't just taken a silica inhibitor that was like developed for reverse osmosis or cooling water treatment that we know works in those applications. We actually had to specifically focus on stuff that we knew was important in geothermal. Thanks, Andrew. So that combination dual active inhibitor is a Solenis development product, and it's actually available for field trials. So those of you on the line who are struggling or have issues with silica deposition, we'd certainly love to hear from you. So we have developed a special testing rig that we're going to be using in New Zealand to develop like further guardrails. In other words, like what is the applicable pH range of this inhibitor that we've developed, and what's the applicable brine chemistries. But yeah, as we say, we're seeking validation sites. So, and Andrew's your main contact point for that. Thanks, Andrew. So in terms of the testing rig, I just wanted to show you this 2 areas about the design of our testing rig. So we take a sample of geothermal brine, we cool it down, right? A lot of people have done that, right? But when you initially cool down your brine, you tend to force precipitation of various minerals. Not all of them will be like classic or high silica related. So we've actually built into this testing rig some detention pipes to give us like 20-30 minutes of retention to allow silica polymerization. If it's going to occur, we want to give it time to occur, and then measure using a test section down the bottom right of that skid design, capillaries, and also an ultrasonic scaling probe to be able to measure the silica deposition after a detention time, which is mimicking a lot more closely what happens in a geothermal power plant. Thanks, Andrew. And again, thanks, Andrew. So what's important then is, like, if you're going to look at like silica inhibitor, you better make sure you know that it's working. And we do actually have a technology which we've actually applied to geothermal situations, which are pretty hot, of course. And in this case, we use an analyzer called an OnGuard 3S unit. And basically, if you have a look at the picture on the lower right, we just allow a stream of scaling fluid to flow past a ultrasonic sensor, and the sensor just really sends ultrasonic waves across to a little reflector plate and back, and it can actually measure the distance very accurately between the sensor, the emitter and the reflector plate. So anything that builds up on the reflector plate, we can measure it, and it produces an output in millimeters per year of scaling. So we think this is going to be very useful for optimizing in the field silica inhibitors. Thanks, Andrew. So in the central North Island, we actually have run one of these, and I'll show just if we have a look at the picture on the left. So that's what you're looking at there is the reflector plate of the ultrasonic sensor, and this is after like being exposed to a re-injection brine for several weeks, not even several weeks, probably about 10 days. And And you can actually see there is the initial development of some silica deposition building up on that reflector plate. It's also building up all over the probe. But the thing is, the chart on the right-hand side shows that the actual ultrasonic analyzer can actually measure that in terms of millimeters. So what we found is, there's slow build-up, and in this case, of course, I was pulling out the probe to actually check it over time. That's why you get a bit of up and down. But certainly after several months, we ended up with like 150, 160 microns of silica deposition. And the important thing was, if you refer to the bottom of that slide, that was actually confirmed as similar to the historic deposition rate for this particular site. So we're very pleased that we can see over a short period of time what's going on. Thanks, Andrew. So for me, that's a short introduction on some mitigation strategies. And I'd thank you for your attention, and certainly happy to engage, offline and afterwards and into the future with anyone who's got questions and wants to learn more about these. Thank you. Over to you, Andrew.
Thanks, Peter. Excellent presentation. So we've got maybe a little over 10 minutes for questions. So as indicated, we would welcome any questions and ask that you submit those via the chat function. And while you're thinking of some questions and submitting those, just wanted to note that Solenis has been very active with global geothermal conferences in 2021. I think we've delivered some 12 papers, a number of those co-authored with customers and fairly significant global or generators, significant generators globally. And that also includes, I think, about 4 or 5 papers that we presented at the World Geothermal Congress back in June. So it covers a number of topics from scale, inhibition, corrosion control, and an area where we've been doing a lot of work and come up with some very novel solutions, and that's around well cleaning and stimulation. So there really is some excellent material available, and we would encourage you to seek these out at the association links indicated here. So we're just looking at the chat. I see that we don't have any questions at the moment. So we'll give it a couple of minutes, and if not, we can give you 10 minutes of your day back. As I said previously, you're very welcome to reach out either via my email address, which you can see there, or through the contact function at solenis.com, and we'd be very happy to hear from you. Still no questions, so I'm assuming that we're not going to get any questions, and therefore we'll wrap up today's presentation. So thank you very much, everybody, for your time. Certainly hope it's been beneficial, and we look forward to interacting with you in the future. Thank you, everybody.
Thanks, folks.
Thank you.